Hello everyone, welcome to a new lecture of our course on processing in memory systems. Today we are going to talk about machine learning training on a real processing in memory system. This work has been recently presented at ISPAS 2023. Let's start with a brief executive summary. Training machine learning algorithms is computationally expensive and memory bound due to the accesses to large training data sets and their iterative nature. Memory-centric computing systems that are systems with processing in memory capabilities can alleviate this data movement bottleneck. And real-world processing in memory systems, as you know, have been manufactured and commercialized since the advent of the PIM architecture. Our goal in this work is to understand the potential of modern general-purpose processing in memory architectures to accelerate machine learning training. And main contributions of this work are the PIM implementation of several classic machine learning algorithms, linear regression, logistic regression, decision tree, and K-means clustering, their workload characterization, and the comparison to their counterpart CPU and GPU implementations. As you will see, the PIM version of decision tree is 27 times and 1.34 times faster than the CPU and the GPU versions respectively. And the PIM version of K-means is 2.8 and 3.2 times faster than the CPU and the GPU versions respectively. Our source code is publicly available. As you will see, we have carried out our experimental evaluation on a real processing in memory system with more than 2,500 PIM cores. And outcomes of this work are key observations, takeaways, and recommendations for ML workloads on real general purpose processing in memory systems. We are going to start briefly talking about the machine learning workloads that we are targeting. Then we will describe the type of processing in memory system that we use in our work. Next, we will detail the PIM implementation of the ML workloads, and finally the evaluation with quality metrics, analysis of PIM kernels, performance scaling analysis, and comparison to CPU and GPU. So let's start with the machine learning workloads. Machine learning workloads, as I said earlier, need large amounts of data to train, and that's the one reason why they are a computationally expensive process. The other reason is that they require many iterations, and this usually causes frequent data movement between memory and processing elements, and sometimes the computation is not enough to amortize the cost of moving the training data due to low arithmetic intensity or low temporal locality or irregular memory accesses. Our goal in this work is to study and analyze how real-world general-purpose processing in memory systems can accelerate machine learning training. And as I mentioned earlier, we have chosen 4 representative ML algorithms that are linear and logistic regression, decision tree, and K-means. We analyzed all of them using the roofline model on a CPU and observed that the 4 of them fall in the memory-bound area of the roofline. Thus, they are good candidates for memory-centric computing systems and acceleration with processing in memory. Processing in memory, as you already know from this course, is a computing paradigm that advocates for memory-centric computing systems with processing elements near or inside the memory arrays. The real-world PIM architectures, as we are studying in this course, are becoming a reality, and examples that we already know are AppMem, prototypes from Samsung, SK Hynix, and Alibaba. All these PIM systems have some common characteristics. First of all, there is a host processor, either a CPU or a GPU, that has access to a standard main memory and PIM-enabled memory. There is a PIM-enabled memory containing multiple PIM processing elements with high bandwidth and low latency memory access. The third characteristic is that these PIM processing elements run at a few hundred megahertz and have a small number of registers and small or no caches and scratchpad. And finally, they typically need to communicate via the host processor. This is how one of these systems looks like, where with the standard main memory, the host processor, and the PIM-enabled memory that contains memory arrays and PIM processing elements. In our work, we use the AppMem PIM architecture that consists of general-purpose processing cores called DRAM processing units or DPUs, and it's fine-grained multi-threaded. Each of these DPUs can run up to 24 PIM threads that are called castlets, and they support 32-bit integer arithmetic natively, but multiplication and division are emulated, as well as floating point operations. Each DPU or PIM core has access to its own DRAM bank called MRAM and its own scratchpad memory called WRAM. This is a picture of the AppMem-based PIM system that we already know, with the dual socket CPU, DRAM DIMMs, and PIM-enabled DIMMs. So now let's talk about how we implemented the 4 workloads for the UPMEM PIM system: linear regression, logistic regression, decision tree, and K-means clustering. They are diverse in terms of memory access patterns, operations and data types, and communication and synchronization needs. For linear regression, which is a supervised learning algorithm where the predicted output variable has a linear relation with the input variable, we have used gradient descent as the optimization algorithm to find the minimum of the loss function. In our PIM implementation, we divide the training data set equally among PIM cores and send this training data set to the PIM cores, and then PIM threads compute dot products of the raw vectors and the weights. Each dot product is then compared to the observed value to compute a partial gradient value. And the partial gradient values are reduced inside each TPU, inside each PIM core, and then sent to the host. We generated 4 versions of LIN. The first one uses training data sets of 32-bit real values that are stored in floating point numbers. The second one uses 32-bit fixed point representation. The values are stored in 32-bit integers. The next one is a version that uses hybrid precision. It uses either 8-bit, 16-bit, or 32 bits, depending on the point of the computation. And finally, there is a version that uses custom multiplication that is based on the 8-bit built-in multiplication that the DPUs have. To compare, to check this custom integer multiplication and compare it to the code that is the default integer multiplication code as is generated by the UPMEM compiler, we can see that if we write these in our C code, it will compile to the code that we see next in the slide. First of all, we need to load individual bytes from either the vector X or the matrix of weights W, and then we perform partial multiplications using the 8-bit multiplier, this mul ul, or mul sh ul. Then we need to perform some additions, including shifting, more multiplication, more addition and shifting, and so on. So it's a pretty long code for just a very single line of code in the C code. So what we did here, because we have some knowledge about what's going to be, if we know, if that's the case, that we know in advance what's the precision that the input vector X requires. In this case, we would be assuming that the values are 8-bit values. We can write something like this in our C code, where we use the intrinsics that the UPMEM SDK provides, and then these translate to a much shorter code, as you can see, where we only need to use the 8-bit multiplier twice, these 2 instructions here. Okay, for logistic regression, which is a supervised learning algorithm that is used for classification and outputs probability values for each input observation variable or vector, we use the Sigmoid function to map predicted values to probability. In our PIM implementation, we follow the same workload distribution as in the linear regression implementation, and we have, in this case, 6 different versions of logistic regression. The first one uses 32-bit floating point numbers and approximates the sigmoid operation with Taylor series. The second one uses fixed point representation and also Taylor series. In the third one, we replace the calculation with Taylor series with a lookup table. And this lookup table might be in SIMDRAM, which is the DRAM bank, or in WRAM, which is the scratchpad. And then we have a version that uses hybrid precision and a version that uses custom multiplication. With respect to the LUT-based sigmoid calculation, we take advantage of the fact that sigmoid is symmetric. So this means that we only need to store in the LUT half of the values, and the LUT size is going to depend on the boundary. In this case, in this example, is 20, and the number of bits for the decimal part of the fixed point representation. We are considering 10 here. For in this particular example, the size of the lookup table will be 40 kilobytes, and this means that it can fit either in the WRAM, which is a scratchpad, or in the DRAM bank. Decision trees are tree-based methods used for classification and regression, which partition the feature map, the feature space into leaves with a simple prediction model in each leaf. In the PIM implementation, we partition the training set among PIM cores, and each of them computes partial Gini scores to evaluate the host splits decisions. The host can send different commands to the PIM cores. The first one is a split commit to split a tree leaf. The second one is a split evaluate to evaluate a split. And finally, min-max, which is used to query minimum and maximum values of a feature in a tree leaf. In these decision tree workloads, it's really important to lay out data in a nice way during the split commit operation so that we can maximize the memory bandwidth with streaming accesses. And this data layout also ensures that the memory accesses will be in streaming during the split evaluate. In K-means clustering, this one is an iterative clustering method used to find groups in a dataset which have not been explicitly labeled, or PIM implementation distribute the dataset evenly over the PIM cores, and then the PIM threads evaluate which centroid is the closest one to each point in the training set. To do so, there is a counter and accumulator per coordinate and per centroid, and using them, the host will recalculate the centroids after each iteration. Convergence will happen to a local optimum when the updated centroids coordinates are within a threshold. That is called the Frobenius norm. Now let's go with the evaluation of these workloads on the PIM architecture. First of all, we are going to see the evaluation methodology. We have used synthetic and real data sets, synthetic data sets for strong and weak scaling experiments, and real data sets for the comparison to CPU and GPU. We have evaluated a PIM system with 2524 PIM cores, an Intel Xeon CPU, and an NVIDIA A100 GPU, and we evaluate, first of all, quality metrics, then performance of PIM kernels, performance scaling characteristics, and finally, comparison to CPU and GPU. This is the admin-based PIM system that we have used in our experiments, as you already know. Let's start with the quality metrics. First of all, for linear regression, we can see here in this plot the training error rate for the 4 different versions. Note that the training error rate flattens after 500 iterations. We continue testing after 1000 iterations. And the first observation is that the training error rate of the 32-bit floating point version is the same as the CPU version, as we could expect. And for the integer versions, the training error rate remains low and close to that of the 32-bit floating point version, as we can see in the plot. For logistic regression, we have evaluated all versions as well, like the 6 different versions with the, and we represent here the training error rate. The first observation again is that the training error rate for the 32-bit floating point version is the same as for the CPU version. Second observation is that the LUT-based versions obtain lower training error rates than the 32-bit integer version, since they use exact values and not approximations, exact values that are stored in the lookup table. And finally, we can also observe that reduced precision data types increase the training error rate, and these heavily depends on the number of decimal numbers in the samples. For example, in these experiments here, we are considering 4 decimal numbers in the input samples, while here we are considering only 2, and in this case, that's why the training error rate is significantly lower. So these are for linear and logistic regression. For decision tree, we observe training accuracy that is only slightly lower than that of the CPU version, and for K-means clustering, they have the same scores and indices than the CPU and the PIM versions. So in summary, we can say that we maintain the accuracy of all workloads in the PIM system, or at least we keep it close to the CPU baseline. Okay, now let's go with the analysis of PIM kernels. These are results for linear regression. As you can see in the y-axis of these 2 plots, we have the PIM kernel time, and in the x-axis, we have the number of PIM threads from 1 to 24, which is the maximum in the PIM cores of the PIM architecture. One first observation is that all versions saturate at 11 or more PIM threads. Another observation is that the fixed point representation accelerates the kernel by an order of magnitude over the version that uses 32-bit floating point numbers. And this takes us to the first key takeaway. Workloads with arithmetic operations or data types that are not natively supported by the PIM cores run at low performance due to the instruction emulation. And that's what happens with floating point operations in PIM architecture. So the first recommendation here is to use fixed point representation. in most of the cases without much accuracy loss if PIM cores do not support floating point. More observations for linear regression is that the hybrid version is 41% faster than the 32-bit integer version. So one more recommendation is to use quantization, which can take advantage of native hardware support and hybrid precision that can significantly improve performance. And the version that uses the built-in multiplication, the custom multiplication that we designed, provides an additional 25% speed up. So recommendation 3 is that programmers or better compilers can optimize code by leveraging native instructions, as is the case of the 8-bit integer multiplication in the PIM architecture. Observations for the logistic regression results. First of all, there is a very high kernel time for the 32-bit floating point and 32-bit integer versions because they use Sigmoid approximation with Taylor series. We need multiple iterations of the approximation algorithm in order to achieve a reasonable accuracy. So the version that provides, that uses lookup tables is 53 times faster than the versions that use Taylor series. So recommendation number 4 is to convert computation to memory accesses by keeping pre-calculated operation results in memory. Either use memorization or lookup tables as we did in these experiments. The hybrid version is 28% faster than the 32-bit integer version, and the version with custom multiplication provides an additional 43% speed up. A general observation over all the different kernels that we develop is that the performance of all of them saturates at 11 or more PIM threads. And this is, as we already know from previous lectures, that in the PIM architecture, the pipeline latency hides the memory latency. So in order to maximize performance, we should make sure that we are using 11 or more PIM threads because that's the way of maximizing the performance. And this is especially true for kernels that behave as or become compute bound in the PIM architecture. The access to data is solved because with the streaming memory accesses, we can have a very high bandwidth, but the pipeline is not that fast. So that's why these kernels behave as compute bound. So takeaway number 2 is that ML workloads that are memory bound due to their low arithmetic intensity in CPUs or GPUs become compute bound when running on processing in memory systems. And one recommendation is to maximize the utilization of PIM cores by keeping their pipeline fully busy. Now let's take a look at the performance scaling analysis. We did a weak scaling analysis from 1 to 64 PIM cores. And one first observation is that the PIM kernel time of linear regression, logistic regression, and decision tree scales linearly with the number of PIM cores. That's not the case for k-means because k-means converges with fewer iterations when we have a larger data set, and that's why we see that the execution time reduces as we increase the number of DPUs in the PIM cores in this weak scaling analysis. And finally, the last observation is that the sum of CPU PIM, inter-PIM core, and PIM CPU data movement takes less than 7% of the total execution time in all cases, so it's clearly tolerable. Those observations for weak scaling are also in line with the observations for the strong scaling analysis for a number of PIM cores between 256 and 2048. First of all, the PIM kernel time scales linearly with the number of PIM cores. Second, there is little overhead from the inter-PIM core communication and the communication between host and PIM cores, as we also observed for the weak scaling analysis. So key takeaway number 3, machine learning training workloads which need large training data sets benefit from large PIM-enabled memory with many PIM cores. And even if the PIM cores need to communicate via the host processor, and it's the case on the PIM architecture, the amount of data movement needed for intermediate results is tolerable. Now let's finish with a comparison to CPU and GPU. For linear and logistic regression, these are the results. And First observation is that the PIM versions in both cases are heavily burdened, but when they use operations that are not natively supported by the hardware. We applied several optimizations to reduce the execution time, and we were able to close the gap with the GPU, but still the GPU is significantly faster for linear regression and logistic regression, but at least the optimizations that we applied provided a significant reduction of the execution time. For decision tree and k-means, we used a couple of data sets. The first one is the Higgs-boson data set. These are results for decision tree and k-means. For decision tree, we observed that it's 27 times faster than the CPU version and 1.34 times faster than the GPU version. And k-means is 2.8 and 3.2 times faster than the CPU and the GPU version, respectively. We have additional implementation details, evaluation results, and observations, takeaways, and recommendations in the long archive version of our work, where you can find some decision results for decision tree and k-means with the Criteo data set. These are for decision tree and for k-means. For the PIM version of decision tree, we see that the speedups have increased with respect to the previous data set. Now it's 62 times and 4.5 times faster than the GPU version. And that's basically because now the data set is larger, and for decision tree, the best performing number of PIM cores is also higher. In the previous data set, it was 1024 PIM cores. Here is all PIM cores, more than 2500 PIM cores in the system. And that's why the speedups increase for decision tree. Not for k-means. The speedups are very similar to the ones shown in the previous slide, but this is because for that data set, k-means, the PIM version of k-means was already using the maximum number of PIM cores. So key observation number 4 is that ML workloads that require mainly operations that are natively supported by the PIM architecture, such as decision tree and k-means clustering, outperform their CPU and GPU counterparts. You can find all details about this work in the long archive version, but you can also access a shorter archive version where we just provide the most relevant takeaways and observations and recommendations. The ISPAS 2023 version is linked from this slide, and the code is also publicly available in our repository. Let's conclude again with the executive summary. In this work, we have analyzed machine learning training on processing in memory systems because these algorithms are typically good candidates for memory-centric computing systems or systems with processing in memory capabilities, because they might be highly memory bound due to the access to large training data sets and due to the multiple iterations that they perform to train. That's why in this work we have studied the potential of general purpose processing in memory architectures to accelerate machine learning training. And the contributions of our work are the PIM implementations of linear regression, logistic regression, decision tree, and k-means clustering. And we have characterized these workloads and compared them to their execution on CPU and GPU, and perform an experimental evaluation on a real memory-centric computing system with more than 2,500 PIM cores. Outcomes of our work are key observations, takeaways, and recommendations for ML workloads on general-purpose PIM systems. This is all for today. If you have any comments or questions about this work, please contact me, and I will anyway see you again in the next lecture of our Processing in Memory course. Thank you very much for your attention.